All right, finally, let's get to use the tools in our toolbox. Example 1. Example 1 says to use the limit laws or anything in the toolbox, and the graphs that are given here, the graph of f is the pink graph, including the pink dot, and the graph of G. The graph of G is the blue graph. So we're going to use all of the tools that we have already. We're going to use these two graphs to evaluate the following limits. These three limits over here, of course, if they exist. So then, let's start with the first one. Here we have the limit as x approaches -2 of f of x plus 5 times g of x. I'm going to be super formal, careful with my analysis so that you really see how we're going to do this, carefully applying the rules that we already developed. So in the first case, we have a combination of sum and multiplication with a coefficient and a function. So one of the rules, the very first one, the very first property says that we can apply the limit to each term at a time. So we would have the limit as x approaches -2 of f of x plus the limit as x approaches -2 of 5 times g of x. Again, I'm going to follow formality. I want to make sure that I don't commit an illegal step. And all of the properties that we have developed, everything that is in the toolbox that I just showed you in the previous slide, these are all valid legal tools that we can use. And I'm going to stick to those tools. Then one of the properties, the other one said that because this is a numerical coefficient, I can bring it right here in front of the limit. So I'm going to rewrite this limit here just as is. And then I am going to write plus 5 times the limit as x approaches -2 of g of x. And I think that now is time to figure out what is the value of this limit using the graph on the right. So this is the limit as x approaches -2 of f of x. So let's see, where is -2? So this is -1, -2 right here. This is -2. And if I look at the limit, does it exist? Let's see. This is a double-sided limit, so I have to analyze the function from the left of -2 and from the right of -2. And I notice in both cases that the y values are going towards 1, and the same thing over here. The y values are going towards 1. So then that limit is equal to 1 right here. Plus 5 times. Now I need to evaluate the limit as x approaches -2 of g of x. So now I'm going to transfer to the blue graph right here. So as x approaches -2, from the left, if you notice over here, the y values are approaching -1. So here is -1. And as x approaches -2 from the right, the y values are approaching -1. I'm going to put a heavy dot over here. So yeah, it seems as if the limit as x approaches -2 right here of the function g of x, that limit seems to be -1. The y values are converging towards -1. So I'm going to write here -1. And now simplifying, this will be 1 minus 5, which is equal to -4. So the value of that limit is -4. But what I want you to focus on is focusing on the step-by-step application of the properties. Remember, this is about being formal. It's not about rushing. It's about being careful at applying the tools that you know you can use. It's like building a house, building something that you know that you have to start from the foundation and then you start working your way up. And you do that with the tools that are appropriate. Example B. Here we have to find the limit as x approaches 1 of f of x times g of x. Now we are approaching 1. Let me circle 1. 1 is right here. So if I want to use the properties according to property number 2, I believe it was for the product, this would expand into the limit as x approaches 1 of f of x times the limit as x approaches 1 of g of x. So when I look at the functions now, when x approaches 1 of f, follow the pink graph, the limit seems to be approaching 2. So that looks good. I can go ahead and replace this with 2. When I look at the other function, the limit as x approaches 1 of g of x, I see over here a gap. That means that if you notice, the one-sided limits are different. So then the limit of g at 1 doesn't exist. This limit over here, unfortunately, this limit right here doesn't exist, does not exist. So if it doesn't exist, unfortunately, I cannot use the properties that we developed because you need to remember the conditions of those properties. For those properties to be applicable, the limit of f and the limit of g have to exist. If one limit doesn't exist, then I cannot use the properties. Now, the limit may still exist, but I'm going to have to figure that out in a different way. I will not be able to use the properties that we just discussed. So then, let me go on to plan B. This property cannot be applied, but I still want to see whether the limit exists after all. So what I am going to do is I am going to work with the one-sided limits. And then I will see if the one-sided limits are equal. If they are equal, then the double-sided limit exists, right? Because they're asking me to find out whether the double-sided limit exists right here. They said the limit as x goes to 1. So then I know that if I analyze the one-sided limits, and if those one-sided limits have the same value, then the double-sided limit exists. Only that I'm going to have to do that separately. I will not be able to use the properties that we just developed. So let's see what happens on the left of 1. So when x approaches 1 from the left, that's going to be case number 1. Remember that the limits, the property of limits that we just discussed, they also apply to one-sided limits. So what I'm going to do is I will try to reapply the same property, but not to the double-sided limit, but to the one-sided limits. So I will consider the limit as x approaches 1 from the left of f of x times g of x. And again, this will be equal to the limit as x approaches 1 from the left of f of x times the limit as x approaches 1 from the left of g of x. And I will try this again. So when x approaches 1 from the left, the limit of f of x is 2. Again, that doesn't change. I'm going to have 2 right here. Now for the other one, when x approaches 1 from the left, right here, the y values of this function are approaching -2 right there. So then that means that I'm going to have -2. So then this limit will be equal to -4. So that becomes my answer. I don't see anything wrong with that. Now, on to the next limit. The limit as x approaches 1 from the right of f of x times g of x. In this case, again, this will be equal to the limit as x approaches 1 from the right of f of x times the limit as x approaches 1 from the right of g of x. And if I analyze the limits again, as x approaches 1 from the right, look at the pink graph, that's f of x. It is approaching 2. So I am going to write 2 right here. And then for the g of x function, as x approaches 1 from the right, the y values are now approaching -1. But again, those two limits exist. So I can use the properties that we just developed. And that is going to give me an answer of -2. Now, what's the problem with that? Look at this. -4 for the left-hand limit. -2 for the right-hand limit. We already discussed in the previous section that if the one-sided limits are different, then the double-sided limit does not exist. So the conclusion will be here that the limit as x approaches 1 of f of x times g of x does not exist. Why? Because the limit as x approaches 1 from the left of f of x times g of x does not equal to the limit as x approaches 1 from the right of f of x times g of x. If the one-sided limits are unequal, then the double-sided limit does not exist. What is nice about this problem is that it shows that we couldn't apply the property to the double-sided limit from the very beginning because the double-sided limit of g of x did not exist. So then we can't apply the property. But the one-sided limit of both f and g do exist. They actually exist. So then that means that we were able to apply the property to the one-sided limits. But then at the end, because the one-sided limits ended up being different, then the double-sided limit did not exist. And that was the final conclusion. All right, so example C. We have to find the limit as x approaches 2 of f of x over g of x. And again, it's a double-sided limit. I will try to apply my properties and see what happens. According to my properties, I can apply the limit separately to the numerator and denominator. I end up getting something like this. And then I look at the graph and see what happens. As x approaches 2, let me locate 2. 2 is right here. This is 2. So as x approaches 2 for f of x, imagine x is going towards 2 from the left and is going towards 2 from the right. It appears as if indeed this is the limit. And yeah, that is the limit. So what we're going to do right now is to try to approximate it. It doesn't fall exactly on the grid, so we can say perhaps 1.4. Doesn't seem to be 1.5. Let's say 1.4. Even if you say 1.3, it should be fine. We are just trying to approximate it. So here it will be 1.4 divided by, now the limit as x approaches 2 of g of x. So now g of x is the blue graph. See what happens over here? When x approaches 2 of g of x is actually crossing the x-axis at 2. So g of x happens to be equal to 0. And immediately, this violates the property, one of the properties, the property involving division. If you remember, the property said that the limit of the denominator cannot be 0. So I cannot apply the property. However, as we did in part B, just because I cannot apply the property, it doesn't mean that the limit doesn't exist. what this is telling me is that because I got 0 in the denominator for the limit of the g function, the property cannot be used to make any further conclusions. But I can always try to see if I can apply the property to the one-sided limits. And then I will compare the one-sided limits. If the one-sided limits are equal, fantastic, then the double-sided limit exists. And if they are unequal, then the double-sided limit doesn't exist. So I'm going to try to do the same thing as I did with part B. All right, so case number 1. What happens to the limit as x approaches 2 from the left of f of x divided by g of x? Let's do the numerator first. As x approaches 2 from the left, the numerator is approaching 1.4, and the denominator, if you notice over here, is approaching 0, but from below the x-axis. So it is going to 0, but it is going to 0 in a negative way. So remember, these numbers over here are going to be negative. Then that means that 1.4 over something that is approaching zeros over something that is getting very, very small is going to be something very, very large, but negative. So this will be negative infinity. Well, that immediately, that is telling us that the limit does not exist, right? Because if you remember, infinity or negative infinity is not a value, it's only a concept. So this limit does not exist. Similarly, I can try to evaluate or to analyze the limit as x approaches 2 from the right of f of x over g of x. And again, the numerator approaches 1.4. And now the denominator, as x is approaching 2 from the right, the function is going towards 0, but in a positive way. So I'm going to put 0 here and a little plus to remind you it is going to 0, but positively. However, a fixed number over 0, something that is getting very, very, very small, is getting very, very, very large positively. So the limit is approaching positive infinity. But then again, from the point of view of whether the limit exists, you have to say no, the limit doesn't exist. So conclusion, the double-sided limit, the limit as x approaches 2 of f of x over g of x actually does not exist. There is no limit. Example 2 is asking us to evaluate the following limits and to justify each step with the limit laws, with the properties of limits that we just developed. In other words, be formal. Don't try to cut corners. So I'm going to go ahead and I'm going to think of each term as a separate function. Imagine f of x is 2x squared, g of x is negative 3x, h of x is constant, is equal to 4. So the first property says that I can apply the limit to each term separately. As x approaches 5, 2x squared minus the limit as x approaches 5 of 3x plus the limit as x approaches 5 of 4. Here I have a coefficient and I have a coefficient here as well. So in my next step, I'm going to go ahead and bring this in front of the limit notation. So this will be equal to 2 times the limit as x approaches 5 of x squared minus 3 times the limit as x approaches 5 of x plus the limit as x approaches 5 of 4. And now I can try to evaluate these limits. These limits are already in our toolbox, all of these limits right here. So then I know that the limit as x approaches 5 of x squared, this will just be equal to 5 squared minus 3 times the limit as x approaches 5 of x is going to be equal to 5, and the limit of a constant is always equal to the constant itself. So then this is going to be equal to 2 times 25 minus 15 plus 4, which is going to give us 39 as the value of the limit. Example or part B of example 2 is asking us to evaluate the limit as x approaches negative 2 of this rational function. So I have a numerator and denominator, but that's not difficult. Now that we have the laws, we're going to go ahead and apply the limit to the numerator and to the denominator separately. So x to the third plus 2x squared minus 1. This will be divided by the limit as x approaches negative 2 of 5 minus 3x. So that's what we have. Then, continuing with the formality of the rules, now this limit is applied to every single term in the numerator and same thing in the denominator. So this will be the limit as x approaches negative 2 of x to the third plus the limit as x approaches negative 2 of 2x squared minus the limit as x approaches negative 2 of 1. All this divided by the limit as x approaches negative 2 of 5 minus the limit as x approaches negative 2 of 3x. So that's what we have. Now let's deal with the coefficients. 2 can come outside, 3 can come outside. Some of these limits we can already evaluate, so we'll try to be efficient that way. So the very first limit right here, this is the limit of a power function. That will be negative 2 to the third. Plus, here, because we're doing formality, following formality, 2 has to come in front of the limit before we evaluate that limit. So 2 times the limit as x approaches negative 2 of x squared minus, and now the limit of this constant function is just going to be 1, the constant itself. So divided by the limit of another constant function. So then this is going to be 5 minus the coefficient comes in front of the limit as x approaches negative 2 of x. Now negative 2 to the third is going to be equal to negative 8 plus 2 times negative 2 squared minus 1 divided by 5 minus 3 times negative 2. So now simplifying, let me continue here. This is going to be equal to negative 8 plus negative 2 squared is 4. 4 times 2 is going to be 8 minus 1 divided by 5 plus 3 times negative 2. That's going to give us negative 6. And because of this negative, positive 6. Now here we notice that the negative and the positive 8 will cancel out. So we're going to end up getting negative 1 divided by 11 as the value of that limit. So nice, so simple. A little bit tedious because of the algebra, but nothing difficult. We didn't have to draw a graph of the rational function. We didn't have to try to approximate the limit by using a table. We did it straight through just with algebra. Part C of this problem is asking us to find the limit as t approaches 3 of t to the negative 1/4 times t plus 5 to the 1/3. This is a product of two functions. This is one function and this is the other function. So I'm going to try to use the product property, the product rule. So then in this case, I know that I can apply the limit to each factor, to each function separately. this will be the limit as t approaches 3 of t to the negative 1/4. And I want you to notice how the exponent is a rational exponent. So we do know how to deal with that limit. Negative 1/4 is like when we were saying P over Q in the properties. And then over here, times the limit as t approaches 3 of t plus 5 to the 1/3. So this is the other one. This first limit right here, we can already evaluate. This will be equal to 3 to the negative 1/4. So that's the first limit, nice and simple. And then the one on the right here, we know that one of the properties says that we can bring the limit inside of the exponent. So we can bring that limit and apply it to t plus 5. So again, let's follow formality here. We are going to have the limit as t approaches 3 of t plus the limit as t approaches 3 of 5, all of this to the 1/3. So that's going to give us 3 to the negative 1/4. And then we know that this limit right here is just going to be equal to 3. And this limit right here is just going to be equal to 5 to the 1/3. So then this will be 3 to the negative 1/4 times 8 to the 1/3. But having 8 to the 1/3 is the same thing as having cube root of 8. So then the cube root of 8 happens to be 2. And then what I'm going to do is to make this exponent positive by bringing it to the denominator. So this will be divided by 3 to the 1/4. And this becomes the value of the limit. Example 3 is asking us to show that the product law or the product property, that I think it was the second property that we developed today, we want to show that we cannot apply that property to f of x times g of x. F of x times g of x, think of it as a new function. Now f is x just by itself, and g by itself is just 1 over x. So let's see, why not? Why can't we apply that property? Let me try to apply it and see what happens. Something is going to go wrong. The limit as x approaches 0 of f of x times g of x. All right, according to the property, if I want to apply it, that will be equal to the limit as x goes to 0 of f of x times the limit as x goes to 0 of g of x. Let's see what happens here. So in the first case, f of x is just x. So this will be equal to the limit as x approaches 0 of x. I am replacing f of x with the expression times the limit as x approaches 0 of 1 over x. And this is what is happening. The first limit, there's not a single problem with that. This answer, the first limit, is going to be 0. But for the second limit, this is the limit as x approaches 0 of 1 over x. This limit over here does not exist at 0. It doesn't exist. As x approaches 0, the denominator goes to 0. So then that means that we are getting the 1 over 0 scenario. So this is going to result in either infinity or negative infinity. Let's look at the graph of 1 over x so that you convince yourself that indeed this limit right here doesn't exist. Look at the graph. This is 1 over x. This is the graph of g. As x approaches 0 from the right, 1 over x is going towards positive infinity. And as x approaches 0 from the left, 1 over x is going towards negative infinity. So yes, this limit right here doesn't exist. That means that we cannot apply the property to this particular function, f of x times g of x. Now, that doesn't mean that the limit doesn't exist. This limit right here may still exist, but we're going to have to investigate it completely separately from the properties. We will not be able to apply the properties. We're going to have to try to apply or do something else. So this is what I have in mind as an alternative. What I want to do is I want to start with the same limit that they're giving us, f of x times g of x. And we're going to go ahead and substitute the expressions right away. F of x is equal to x, and g of x is 1 over x. And now you notice that the x's will cancel each other out, and we will end up with the limit as x approaches 0 of 1. So practically what is happening is the following. F of x times g of x is just equivalent to 1 as long as x doesn't equal to 0. So this is true provided x is not equal to 0. But remember, we want to investigate what is the limit as x approaches 0. And a limit can exist at 0 even though the function is not defined there. So in this case, when I continue, the limit as x approaches 0 of 1 being a constant function, will just equal to 1. And this is the value of the limit. So this function, f of x times g of x, actually ended up having a limit after all. The limit is equal to 1. And pictorially, you're going to see that it makes perfect sense. Here is a picture of f of x times g of x. And what happens is that the function pretty much is horizontal at a height of 1 with an open circle here, telling us that when x is equal to 0, the function is undefined. But this is a question about limits, so we don't care what happens at 0. Around 0, to the left of 0, the function is exactly 1. And to the right of 0, the function is 1. So no wonder the limit ended up being 1. So a great example where we couldn't make any conclusions with the properties that we developed in this section because this limit by itself did not exist at 0. So if we change gears and we look for another way, then you can easily conclude that yes, the function has a limit, or sometimes no, the function actually doesn't have a limit. In this case, we were very lucky and we found a beautiful real number as the value of the limit.